So someone tell me, what is Newton's first law? Carissa? Excellent, excellent. Now we're going to focus today on that last statement, right? So an object at rest stays at rest, an object in motion will stay in motion unless acted upon by an unbalanced force. And what is an unbalanced force? This is a force that is not balanced by one of equal and opposite magnitude. So take the example of this marker here on this table, or myself on the ground. Why am I not flying up into the sky or falling down to the center of the earth? Sorry, anyone? Yeah, exactly. So I am pushing down on the ground with a force, my weight to be particular, and the ground is pushing back with an equal and opposite force. That's why I don't spontaneously fly up into the air or go to the center of the earth, right? So those forces would be equal and opposite. They are balanced. Now, if I wanted to apply an unbalanced force to, say, this remote here, I could give it a little shove. Now, when I gave it a little shove, what did I do to its state of motion? State of motion is the object's velocity. What did I do to its state of motion? Did its velocity change when I shoved it? Yeah, and what do we call a change in velocity? Acceleration, excellent. So what can we say an unbalanced force does? What does an unbalanced force do to an object? What does it cause? It causes acceleration, right? That's a massive concept. So today we're going to be focusing on just practical, is there acceleration, is there not acceleration, aka, i.e. is there a balanced force or an unbalanced force? But next class we're going to be figuring out the math behind that. How do we calculate the acceleration? So, these are two examples here, kind of what I just talked about. If we place a physics textbook on a table and it's at rest, not moving, well, the forces on that object must be balanced. Now, if I gave that textbook a shove, right, or I gave this remote here a shove, well, it's going to accelerate as it's in contact with my finger. And then as soon as it leaves my finger, what happens to it? It slows down. There's another unbalanced force. What is the unbalanced force when it's slowing down? Cooper, you nailed it this morning. What was it?
The drag on the table and through the air. Exactly.
Friction. Friction. So I'll give you a lot of air resistance for moving super slow, but friction with the table, right? So those are two examples of unbalanced forces. Whenever you change your state of motion, whenever there's a change in velocity, aka acceleration, you have an unbalanced force. So that is a pretty key point. You may want to asterisk that and just write in an unbalanced force causes acceleration. So here's two examples that are far less intuitive than the textbook or the remote I was talking about. Because I want you to think about velocity for a second. Is velocity a vector or a scalar? Yeah, it's a vector, right? So vectors are described by what?
Direction.
Magnitude and direction, right? Magnitude and direction. So would a change in direction also be the result of an unbalanced force? Yes, right? Yes. So changing direction is acceleration. It is the result of an unbalanced force. And these are two beautiful examples of this. I'm a little impartial when it comes to space exploration, in that I love it beyond all else. So we're going to do quite a few examples in this unit that revolve around outer space and satellites. Now, if this is planet Earth here, my beautiful depiction of Earth, there's some continents. I don't know, take your pick. Some more continents. How does a satellite work? Why doesn't the satellite just shoot off into space? Why does it orbit the planet? Cooper?
Because there's gravity pulling, keeping it in a little bit.
Yeah, that's right. So if I have an object here, here's my satellite. We're going to give it some solar panels. And my satellite, we're going to say, is traveling in this direction at, I don't know, let's say 10,000 kilometers an hour. Now, the reason it doesn't shoot off into space is because you're right. What does our planet do?
Keep it pulled in.
It pulls on it, right? We have the force due to gravity. So we have our object zooming this way super, super fast, but there's a force acting on it, and that's the force of gravity. Now, really what's happening is our object is going to be accelerating towards the planet. Why doesn't it ever hit Earth? What would happen if we started to slow this object down? Do you think it would hit Earth? It would. Yeah, really satellites that are in orbit, they are just narrowly missing our planet at all times. Right? They're moving fast enough such that this acceleration towards the center of the Earth will keep it in orbit. Now, what happens if I speed this object up a little bit? Yeah, the orbit might get a little bit bigger. If I slow it down, the orbit might get a little closer to Earth. In fact, if I slow it down too much, the orbit will cause the satellite to enter the atmosphere and burn up. Now, really what's happening is our object is continually accelerating to the center of our planet, and it's just narrowly missing our Earth. That's what satellites do when they are in orbit. So that's a good example of an object that has a constant speed, but has a continually changing direction. And as a result of that, there's an unbalanced force, which is the force due to gravity. Now, a more easy example to wrap your minds around might be highways. If we look at our highways around Manitoba, how do they prevent you from flying off the road when you hit a corner? Cooper?
They got like barriers on the side.
They have barriers. Some do.
And speed limits.
Yeah, sometimes they reduce your speed. The most extreme example of what I'm going to talk about has to be like the Daytona 500. Has anybody here ever been to a NASCAR track before? You have, Carissa? Have you ever stepped out on it? How steep is the track? You don't know? Okay.
Well, it curves around the corners, but...
Yeah, when you go around a corner, in fact, it's so steep, like, I didn't realize how steep it was. It looks like you can barely climb up the thing, right? It's like crazy steep. So, let's say we had a completely flat highway, right? So, there's no change in the elevation of the road surface, so it's just a flat highway, and we have a car that is moving in this direction here. So let's say this road is really icy, okay? It's super, super icy. What's going to happen to our car? Right, inertia. Objects tend to resist changes to their state of motion. It's going to keep doing what it's doing. So where is it going to go? Yeah, you're going to go into the ditch, right? You're going to keep traveling, and you're going to go into the ditch. You're going to turn your wheels, but it's black ice. You're just going to go straight into the ditch. Okay? Now, what we do to prevent this on our highways is we bank them. So if I looked at a cross-section of our highway, it would look something like this. So this is a cross-section of our highway. Here's our car. We're looking straight on to our vehicle. And as it goes around the corner, we bank the road. So what is the unbalanced force here? What's going to happen? Well, what's gravity going to do? If this was a ball, what's going to happen to the ball? Is it going to roll down the hill? Right, so we have an unbalanced force here due to gravity, right? So we have an unbalanced force here due to gravity that's going to pull the car towards the inner side of your road here, and that's what keeps your car on the highway. Does that make sense? So we bank the corners so that we can get around them safely. And I said the most extreme example is like a NASCAR track. When I was at the Daytona 500, the track's like that. It's crazy. It's super, super, super steep. And that's to keep the cars on the track. Because if it wasn't that steep, what would happen to the cars? Yeah, they'd have to slow down a ton, otherwise you're going to crash into the barriers or go into the audience. Both of which would be bad. So all of our highways are designed to be safe to transgress at those speeds, even when road conditions aren't fantastic. Obviously, if there's black ice, you probably still shouldn't be going speed limit, but they are banked so that you can safely make those turns. So those are two less intuitive examples of an unbalanced force, because they are causing you to change directions, not necessarily causing you to change speed. So velocity is a vector, has magnitude and direction, and therefore if you're changing direction, you are causing an acceleration, and therefore there is an unbalanced force. So what is a force? What is a force? Now, we kind of think of them as a push or a pull on an object, resulting from an object's interaction with another. Now, this isn't completely accurate because there are forces that happen at a distance, which we're going to explore. I just showed you one. What was a force at a distance that affected our satellite? Yeah, gravity, right? Now, when there is an interaction between two objects, there is a force upon each of the objects, and when the interaction ceases, the two objects no longer experience the force, right? When I am pushing this remote on the table here, I'm only exerting a force on it while my finger is in contact with it. Once it leaves my finger, the force is no longer being exerted. Now, forces only exist as a result of this interaction. Now, there's going to be two main types of forces that we are going to explore. One is going to be contact forces, the one I just described to you, the one you are most familiar with, right? You punch someone in the face, that is a contact force. You push something, that is a contact force. You pull something, that is a contact force. Now, other ones that you may not be familiar with, frictional forces, right? Friction always opposes motion, so as soon as I stop pushing this remote here, what slows it down is friction. When I'm skydiving, the contact of air particles causes air resistance. That is a type of friction. Another one here could be tensional forces, like you're tugging on a rope, and the tension in the rope is the force. Normal force is just the force that opposes gravity, so me standing on the ground is pushing back with that same force. That is called the normal force. Air resistance, and then applied forces is the one you are most familiar with. That's like your literal contacting, punching, pushing, pulling, that type of force. Now, what other forces at a distance can you think of? So gravity is a good one. Can you think of any others? Sorry? I can't hear you. One second.
Wind.
Did you say waves?
Wind.
Oh, wind. No, wind I would say is a contact force. What's causing you to feel that wind? Yeah, the air around us is composed of matter. It's particles, right? So the wind is literally those particles hitting you, and you're feeling the force. Anybody here ever seen like an auto wrecker? What do they use to like pick up scrap metal and stuff like that? Yeah? Yeah, like magnetism would be another good example. Now there aren't many action at a distance forces that we're going to explore this year. In fact, the only one we're really going to be exploring is gravitational forces. The other two, electrical, magnetic, you have a heavy focus in grade 11, 12 physics. Now, on your worksheets, you're going to see what are called free body diagrams. So I'm going to show you a brief example here of what a free body diagram is. So you may want to write this down. So a free body diagram shows the relative size of the forces acting on an object with arrows. And traditionally, when we draw an object, I'm a very, very amazing drawer, horrible drawer, and most physicists don't like drawing too much, so guess what we draw everything as? We draw them all as the same thing. One of your fundamental shapes. Yeah, everything gets reduced to a square. So when we draw any object in physics, we pretty much just draw a square. I'm sure there's a really good cheesy science joke there I'm missing. How we're not hip, we're squares. Anyways, now when we're drawing these forces, these force vectors, because force, by the way, is another vector quantity, right? These arrows represent force vectors. Their size actually indicates how strong that force is. So, if I were to draw an arrow that looks like that, and I were to draw an arrow that looks like that, what can you say about the forces acting on this object? Yeah?
Stronger going to the right, so it's probably moving towards the right.
Ooh, not necessarily moving towards the right. You're right, there is a force to the right, yeah? It is unbalanced, you are right. And if it's unbalanced, what does that mean? There is an acceleration. So in this case here, we do have an unbalanced force, therefore there is an acceleration in which direction? Yeah, there's going to be an acceleration that way. Does that make sense? So we have an unbalanced force to the right here, so there'll be an acceleration to the right. So in this example here, there is an unbalanced force to the right. And therefore, our acceleration is to the right. Now, it doesn't necessarily mean, Cooper, that we are traveling to the right. Right? We explored many examples where we had objects that were traveling one way and acceleration was in the opposite direction. So this could be an object that is speeding up to the right. You're right. Right? It could be an object that's traveling right and speeding up. But what else could it be? else could it be? Yeah, this could be an object that's traveling left and slowing down. Does that make sense? Right? Acceleration does not tell you which direction the object is moving. It just tells you how your velocity is changing. So we could be moving this way and slowing down, or we could be moving this way and speeding up. Either one's correct. Now, when we have an unbalanced force, I wasn't sure if I was going to introduce this today, but I think we will. We call this a net force. So we call this a net force. So a net force is once you cancel out all the forces, there's something left over, right? Is the resultant unbalanced force, or I should just say the resultant force once all forces are, let's say, canceled out. Once all the other forces are canceled out. So what do I mean by this? Well, if I took this force here and I canceled out from here, how much left over do we have? So if I take this force here, let's say that this force is, I don't know, we'll say that this is like 20. And again, the unit we're going to be talking about here is newtons. But don't worry too much about that unit today. We're really going to talk about that tomorrow. And let's say that this is 50 newtons. How much left over once we cancel it out do we have in that direction? Yeah, it would be 30, right? So another way, when we write net force, by the way, we will write it like this. That weird Greek kind of epsilon looking symbol there. So your net force we represent like this, and in this case, your net force, by the way, this means the sum of all. That's what that means. It means the sum of all. So the sum of all forces is going to be 30 newtons to the right. All right, so the sum of all forces here will be 30 newtons to the right. So let's just explore one more example here, and then I'll let you work. So don't worry today too much about these numbers. We're really going to start exploring these more in the next couple lessons. Today I just want you to understand that an unbalanced force causes an acceleration. And what is an unbalanced force? How do we know if there's an unbalanced force? What do we got to look at? Sure, we could physically look at the object and see how it's changing its state of motion, or is it slowing down, speeding up. But we need to look at the forces on our object and see if they cancel out, right? Because if I gave you, let's say an example like this. Let's say instead I had an object that was like this. So we had a force like that, and a force like that. We're going to say that each of these forces is, say, I don't know, 20. But then we had a force like this of, like, say, like 40. You know what, let's make this a little more interesting. Let's make that 10. So, if I wanted to know if there's an unbalanced force on this object, I got to cancel out all my forces, right? I need to see what's left over once we see if things are balanced out or not. So let's first look in the left and right direction here. Are these forces equal and opposite to one another? Yeah, they are. So are those forces balanced? Correct. Those forces would be balanced. So we do not have acceleration either left or right. How about up and down? Are those forces balanced out? No. How much leftover do we have once we cancel out? In which direction? Down. Right? So we can say that the sum of all forces, our net force, is going to be 30 down. Yeah?
What happens if it was unbalanced left and right and up and down?
Excellent question. We will never deal with a situation like that in grade 10. So in grade 10, we only look in one direction. So you'll never encounter that. That's grade 11 physics. So as soon as you have an unbalanced force in multiple directions, now you have to bust out good old trigonometry to figure out the resultant direction of that force. Does that make sense? So if that didn't make sense, don't worry, because you're not going to see that in grade 10. So grade 10, we're just going to be looking at resultant forces, unbalanced forces in a single direction. By the way, I also will often write net like this as well. So your net force could also be represented like that. Now, what would you say in regards to the net force in your left and right direction? Is there a net force to the left or the right? An unbalanced force? It's zero, right? And sometimes you will get problems like that. You know, the example of me standing on the ground, there is currently no net force acting on my body. My force due to gravity is the same as the ground pushing up on me, the normal force. They are equal and opposite to one another. All right, now let's explore an example, you know, in a way that you've seen motion represented before. So, looking at the dot diagrams, oh, by the way, through marking your labs, it's apparent some of you still don't fully understand dot diagrams. Hopefully this will clarify it a bit. Now, if we have an object that is doing this, how would you describe the force acting on this object? Keep in mind, your velocity is in this direction. How would you describe the force acting on this object? What direction would the unbalanced force be if there is one? To the right. Why to the right? Ah, good job. Your vehicle is speeding up, right? Your object is speeding up. How do we know that our object is speeding up? They're getting further and further apart as time goes on. Remember, covering more distance per unit of time. So our acceleration is that way, which means that our force is that way. Now, what if I showed you motion in a different way? What if I said that your object, let's do a position time data. Let's say that you had an object that did this. You had an object that did this. How would you describe this object's motion? Oh, good job, Yvonne. Has a constant speed. What is the speed here, the velocity? Our velocity is 10 meters per second. Is there an acceleration? No, so how would you describe the forces on this object? Would you say they're unbalanced, or would you say they're balanced? All the forces must be balanced, because is there acceleration? No. So our net force, our sum of all forces, must be zero, because there is no acceleration. One more example. Let's say
It's moving, so there has to be some
That was my trick question you asked about at the start of class today, right? The 2 meters per second on the frictionless plane, right? Imagine this marker is in outer space, right? And I give it a push. It's moving at 2 meters per second. Will it continue moving that speed forever until it interacts with some sort of astronomical body? You better believe it's going to be moving that speed forever. So if we have an object that has no acceleration, there is no net force. You're right, we might be pushing that object, but there might be an equal and opposite force like air resistance or friction, or maybe someone else pushing it in the opposite direction that balances those forces out. That doesn't mean there isn't a push or a pull, it just means that there's a force that is equal and opposite in the other direction.
But if the forces are equal, then it wouldn't be moving.
Yeah.
Not necessarily. If all of the forces balance, that just means your object has no acceleration. So if you are moving and all of your forces balance out, that just simply means you are not changing your speed. Just like my example of my marker out in outer space. There's no net force acting upon it, therefore it will never change its speed. Yeah?
So an unbalanced force is just acceleration?
Correct. If your object is accelerating, you have an unbalanced force. Carissa, you look...
You keep using the outer space example, but we're not in outer
Sure,
space.
let's use an example where we're not in outer space. Let's say your car is on, you're on the road, you're driving, okay? So here's your car. I just didn't want to introduce too many confounding variables is why I keep using outer space. Here's your car. Now let's say your velocity is 100 kilometers per hour and your acceleration is 0. So you have reached your target speed, right? You're on the highway, you're traveling 100 kilometers per hour. Now, does that mean there is no push or pull forces here? Of course not, right? What happens if you let off the gas pedal? Yeah, friction's going to start slowing you down, right? Friction will start slowing you down. And that frictional force will be air resistance and obviously all of the friction that's in the components of your vehicle, the gears, everything else, and friction with the road. So there is a force of friction on your car, okay? And that's friction within the mechanical components, air resistance, all of those things. And if we let off the gas pedal, we would have a net force. We would start to slow down, so our net force would be that way. But if we have a constant velocity of 100 kilometers an hour, our acceleration is 0 because our velocity is not changing, and therefore there must not be a net force. What's counteracting this force of friction? The force of your engine, right? So the force of my engine, whatever that is equal and opposite to the force of friction in this case, right? So we can just assign, it doesn't really matter what the values are. We can say that this is, 30 and 30 or whatever. But you can have an object that has no net force, despite the fact that there is a push and a pull force present, right? As long as they equal each other out, you will have no acceleration and no net force. Does that make more sense? Yes? Cooper, you good on that one? Yep. So, in order to have a change in your speed, there must be a force, and that change in speed is acceleration. So unbalanced forces cause acceleration. If there is no acceleration, there is no force, unbalanced force present. That doesn't mean there isn't forces present, there just isn't any unbalanced force present. We're going to be playing with this idea of force and balance a lot. So if you're struggling right now, we're spending a lot of time here, okay?